Hi there, my name is Sajadola and this is my IoT low level assignment for the module Comp 4000. We'll start off by talking about Zephyr and BLE devices. Now these two technologies are what underpin our project. So Zephyr, it's an open source platform. It is intended for use in real-time operating systems or RTOS for short, for connected devices with constrained resource. So that would be a limited amount of CPU power or RAM or storage. Its open source nature has made it attractive for many OEMs who can contribute to the platform, and by using Zephyr, it can reduce their own development costs and thereby accelerate the time to market for billions of connected embedded devices. The main advantages of using Zephyr is that it is modular and supports multiple architectures. Improvements to it are frequently delivered to incorporate enhancements in security, device management capabilities, connectivity stacks, and file systems. Onto BLE or Bluetooth Low Energy. This is a new technology that consumes very little power. It is very easy to integrate and connect with, and it's intended for use where you're exchanging small amounts of data. So this is very perfect for the new IoT connected devices with thermistors, smart heating, this kind of sensors where you need to exchange small amounts of data. We'll just talk a little about what GAP and GAT is in terms of Zephyr and the system. So GAP defines the general topology of the Bluetooth Low Energy network stack. There are two mechanisms a BLE device can use to communicate to the outside world. The first one is broadcasting and the second one is connecting. These mechanisms are subject to the General Access Protocol or GAP guidelines. GAP defines how BLE embedded devices can make themselves available and how two devices can communicate directly with each other. On the other hand, GAT describes in detail how attributes or data are transferred once the device has a dedicated connection. GAT specifically focuses on how data is formatted, packaged, and sent according to its described rules. GAT uses Attribute Protocol, or ATT for short, to describe how data is exchanged from two connected devices. ATT protocol is concerned with the representation of data attributes in the BLE server database and defines the transaction activities on them, either when they are delivered successfully or not. On the right-hand side, we show a BLE protocol stack, and as we can see, it is divided into three main parts: the controller, host, and application. The generic attribute protocol and the generic access profile lie in the host layer. Now we'll talk a little bit about GAT read and writes. So each attribute that we have declared can have one of four access permissions. They are none. So if you set it to none, the attribute can neither be read nor written by a client. If you set it to readable, the attribute can be read by a client. If you set it to writable, the attribute can be written by a client, while if you set it to readable and writable, the attribute can both be read and written by the client. Now on to notifications. We use notifications, so we use the app, and when we press the button, we get a notification. So to understand how this works, we must remember that a client initially knows nothing in advance about a server's attributes. So it will need to perform discovery to find out which services, characteristics, and descriptors are present in the server. A notification is an unacknowledged message. These notifications are sent anytime the relevant data in the GAT table on the GAT server is updated. To get these notifications, you must subscribe to the data. So the way we subscribe is by pressing the button in the app, and we get an update on the terminal. Now on to the circuit diagram of our project setup. So we're using the SCD30 sensor, which has the CO2, the temperature and humidity. We've connected it up to the BBC Microbit version 2, which has an LED matrix module attached to it. We've connected it to the serial. We've connected to the PC to view the GDK terminal via the serial port. And we've also connected an analyzer to view the channel 1 and channel 2. So as the microbit communicates with the sensor, we can view the sort of communication information that's sent in between that by connecting channel 1 to the SDA connection and then channel 2 to the SCD connection. Here's just a list of sources that we've used to present this information. In this part of the video, we will take a look at the demonstration video that I've created. So to start off, this is the start of the video. Over here, we have connected the analyzer, which uses pulse view to analyze the SDA and SCL signals. Over here is the sensor, and over here is the LED, all connected up together. So right now, the LED matrix is showing a smiley face, which means that the parts per million is below our threshold. So we'll just take a look at what our threshold is. Our threshold is set to between 0 and 680. So if the parts per million is below that, it's going to put down a happy smiley emoji face to the LED matrix. And if it is greater than 681, it's going to put in a emoji unhappy. Back to the video, and there is our BLE set up there on the phone. Over here, we're looking at all the measurements taken in the GTK terminal, so we can view the values. So here's the CO2 values, here is the temperature, and over on the other side, the next over here is the humidity. So right now, I'll just go back a little bit. So right now, the parts per million over here is showing up as below 680, so that's why the smiley face is showing. Here's our phone connected to the Bluetooth Low Energy. We've just pressed a read and we are getting it in our GTK terminal, the value. So the value from the GTK terminal, when we press the button on the app, is 660, and that is the same value as the value showing up in the GTK terminal. So now what we've done there is we have taken off our mask and put a little breath onto the sensor, so the CO2 will go up, and as the CO2 goes up above 680, it will hit the threshold and then it will display the unhappy emoji face. So over here, this value 932 is above the 680 threshold, and as you can see, as it's reading it in, it's sensing that it's way above the threshold over here, and it's displaying the unhappy emoji face. Now we're going to press the read value to see what the CO2 value is, and the CO2 in the attribute is 1038 parts per million. So that's all working correctly as intended. So the CO2 is still above 800 there, so it's still going to show the unhappy face there. And I think we'll just let it go down, and we will show that it goes back down to below the threshold, and the smiley face will show back up again. So that was unhappy face we just saw there, and it should go back down now. So as you can see there, it's working perfectly as intended. 676, that's way below the threshold, and it's working as intended. And just one final read, 653, it's way below, so it's working there. 663 there, sorry, there. We'll just take a look at the code for a tiny bit. So we've opened up the code in Visual Studio over here, just to show the if-else statement, the logical reasoning for turning on happy the matrix. So if the parts per million goes between 0 and 680, it puts the matrix.put small function, it calls this function, and if it's above that, it calls unhappy code. So we just declared them in matrix.h, and then in matrix.c we've created the functions. So we've written all the binary 1s and 0 codes to make that happen. Just a little bit about how I got the binary 1s and 0 codes. So we have put a little description over here on how I have gotten the codes. So for example, it's a 5x5 LED matrix over here. So we just created a 5x5 image over here to show you. And we've labeled each LED area with a letter. So A, B, C, D, E, F, and G. So for example, to get LED matrix LED A to light up, we set the the code for the row is 00010, and then the code for the columns to turn this specific LED on is 00010. And so that's how we get the corresponding codes for each of these LEDs to light up. We put them all in here within a for loop so that it loops around for at least a couple of milliseconds so that's visible to the eye. So we are displaying it for just over 4,000 milliseconds. And the same goes for the unhappy emoji face. So this is how we've gotten the corresponding binary 1 and 0 rows and columns code. And here we've placed it within a loop, and we're just displaying it and putting it to sleep for 2 milliseconds. So that's the code, and we'll just go over to what the SDA, the the analyzer, picks up. So the SCL is just a serial clock line for the internal communications, and then the SDA is the data line. So this is just an excerpt from our, as we were doing it, I took a screen snip. Everything here begins with a start signal, so the SDA line goes to ground. That's what starts everything up, and then the peripheral address is sent, and then this bit over here is either a 1 or 0 to represent a read or a write. So this is a W, it's a write, it's sent to 0. And then an acknowledgement is sent, so that it acknowledges that all this has been done, and then the peripheral register is sent through. So this is the binary 1s and 0s. Here we can see the highs and lows of the SCL signal. And then over here we start up everything again. We set the SDA to ground, and we set up all the connections over again. This time we're setting the read and write bits to 1, so it's a read for this address, and then it just sends an acknowledge for this data peripheral. So this is the data that's coming through. This is the data that we're going to be reading. It sends an acknowledge. This is the data, so you can see the binary 1s and 0s, and this is the data read. This is the hex 01, the hex 00, hex B0, and that's it over again. And then over here, after a short little time, everything starts over again. So it sends the start signal again,